I'm here to discuss the residue theorem, which says if you have an integral of a nice function around a nice curve, you can solve it by just looking at the singularities inside of the curve, and then figuring out the residue, which has to do with the Laurent series. It's the negative one term coefficient of the Laurent series, multiplying by 2 pi I. And I'm gonna sketch out a proof for this by drawing a picture. So the picture I'm going to draw is I'm going to have this, let's say this is gamma. Gamma is this kind of dark blue thing. And let's suppose that n is positively oriented. Let's suppose there are only two singularities inside here. Those two. Let's call this one z1. This one will be z2. Well, remember, an integral, all an integral is I'm going to go around each point of the curve. I'm going to plug that value that's on the curve into the function, and I'm going to add it up. That's conceptually what an integral is. So I won't change the value if I add 0 a bunch of times. So I can add 2 circles, one around each singularity, and I can do that as long as I cancel them out by taking the same circle. These should actually be overlapping, but it's tough for me to draw that and still have it be legible. And these are going in opposite directions. So the green circles go counterclockwise and the orange go clockwise, so we cancel each other out. Very similarly, I can draw 2 lines from the curve, and then I can have the same line going in the opposite direction. So what I've done is I'm going to calculate the integral that I want around this dark blue curve gamma, but I'm going to add 0 to it in the form of this green and orange, 0, green and orange, this 0 in terms of blue and purple, and 0 in terms of blue and purple. So I haven't actually changed the value of the integral, but I've changed how I can think about this. That is, this curve I can now think of as a shape that looks roughly like this. Except when I get right here, instead of keep on going here, I'm going to take the purple curve down. Purple curve is going to go down. I'm going to go around the orange circle. I'm drawing this kind of an exaggerated way. And then take the blue back. Now I go back to the dark blue, and I repeat the same process. And then I go purple in, orange circle. I said orange circle. There we go. And now light blue back. So that takes care of everything except for these orange circles, or these green circles. So this is going to be plus the 2 green circles around the singularities. That's Z1, that's Z2. And so I've covered everything. I've just kind of thought about how I do it differently. In particular, note that this thing, I basically, on the interior of this curve, I don't have the singularities, because the singularities would be here and here, but they're outside the curve. So the function f is holomorphic here, and so the integral around this part is equal to 0 by Cauchy's theorem, because the function's holomorphic there. So the integral around my original thing is equal to the integral plus 0 plus 0 plus 0 plus 0, and I can think of it as this the integral around here, which is 0, plus the integral around these two things. Well, I can figure out the integral around these two things pretty easily, right? I just take the integral of, over this curve of the Laurent series, which is going to be c negative 2 over z minus the singularity z1 plus c the negative 1 over z minus z1 plus c0 plus c1 z minus z1 plus dot dot dot. Right? We've seen before that I can integrate term by term, and the integral of all these terms go to 0 except this one, and the integral of 1 over z minus z1 is equal to 2 pi I, and then I just multiply by c minus 1, which is the residue. And very similarly, this is just going to be 2 pi I times maybe d minus 1, which comes from the integral d minus 1 over z minus z2, plus a whole bunch of stuff I don't care about on either side. And so the value of the entire integral is just 2 pi I times d minus 1, c minus 1. These two are the residues. That's exactly what the formula says right here. That's how the proof goes. I hope you enjoyed it.